Characteristics of fine soils. Silt is very small particles of disintegrated rock. So it's very similar to sand and gravel, it's just a smaller particle size. But on the other hand, clay uh, forms as a result of chemical reaction. So it represents chemical changes that have resulted from decomposition and alteration of the original rock minerals. So this is the chart for classification of fine-grained soil, where from the step 1, by looking at percent passing from sieve number 200, we decided that more than 50% is passing through sieve number 200. So more than 50% of particles are fine particles, and as a result we call this soil a fine grained soil. So more than 50% passing sieve number 200, and this means that we have a fine grained soil. When we have a fine grained soil, what is important for us is the plasticity of soil. So in order to evaluate plasticity of soil, we need to look at liquid limit. So step 2, when we have a fine grained soil, is to look at the liquid limit of that soil. If liquid limit is less than 50%, we have low plasticity, and we will use letter L. If liquid limit is equal or higher than 50%, then we have material with high plasticity, and we will use letter H. And then in step 3, we need to figure out if we have more clay or silt. So if our soil sample is mostly consisted of clay or silt. And in order to do that, we need to use plasticity charts. So in this step, we need to use plasticity charts and see if using LL, PL, calculate PI, and then see if our point plots above A line or below A line. So just to go over the chart that was in the previous slide, step 1, we'll look at percent passing from sieve number 200. Now in this case, when we have a fine-grained soil, our answer to the question less than 50% finer than sieve number 200 or less than 50% passing through sieve number 200, our answer is no, more than 50% is passing through sieve number 200, which means that we have a fine-grained soil. So the next step for us is to check the plasticity. If liquid limit is less than 50%, then we have low plasticity, and we will use letter L. And if liquid limit is equal or more than 50%, then it means that we have material with high plasticity, and we will use letter H. So with fine-grained soil, we will look at liquid limit less than 50%, equal or more than 50%. We need to answer the question, do we have high organic material, high content of organic material? If the answer is yes, we have organic silt or organic clay? If the answer is yes, we have organic silt or organic clay. If the answer is no, then you need to calculate plasticity index, plot your point in the plasticity chart, see which one of these statements are satisfied, and then come up with your final symbol. Example number 3, we have the results from sieve analysis and results from liquid limit and plastic limit, Atterberg limits test. First, step 1, we need to look at percent passing from sieve number 200 to see if we have a coarse-grained soil or fine-grained soil. Percent passing from sieve number 200 is 76%. Less than? No, 76 is more than 50%. So the answer to the question is no, which means that we have a fine-grained soil. Now that we have a fine-grained soil, again, what is important for us? Plasticity. So in step 2, we need to look at liquid limit. Liquid limit of the soil sample was 60%. Liquid limit less than 50%? No, it's more than 50%. Which means that we have fine-grained soil with high plasticity. So we will use letter H. Now in step 3, we need to answer the question, is this organic material? In the first slide of this example, we had inorganic soil, so the answer is no. And our options are high silt with high plasticity or clay with high plasticity, which also referred to as elastic silt or fat clay. To find the final answer, or our step 4 is to use plasticity chart. So this is our plasticity chart. We have the results from Atterberg limits. Liquid limit of the soil sample was 60%, so that's our liquid limit. We have LL and PL. We can calculate PI as LL minus PL. So our plasticity index is 32. And we can find our point. The point is, so this is LL 60% and PI 32%. This is above A line. So this one is satisfied. Also PI is 32% and it's above 7, which means that both of these statements are satisfied, and we can say our final answer is CH or fat clay. This is another example of a plasticity chart. What you need for this class is to use A-line for your examples, which is this one. But you can also see the formula for A-line when your point is very close to the line and you don't know, you cannot decide if it's above or below. You can actually use the formula to see if it's above the A line or below the A line. Okay, so for coarse grained soil, we will have gravel and sand. If we have clean gravel, then we can have a well graded gravel or a poorly graded gravel. These are with little or no fines, less than 5% of fines. Then if the amount of fine is higher, then we need to know if it's silt or clay. So the options are now silty gravel or clayey gravel. Same thing for sand. If the amount of fine is less than 5%, then we have clean sand, which can be a well-graded sand or a poorly graded sand. But if the amount of fine is higher, then it's important for us to know if it's silty sand or clayey sand. And if we have fine grained soil, which is basically silts and clay, then what is important for us is plasticity. So we look at LL. LL lower than 50 means we have material with low plasticity. LL equal or higher than 50% means that we have material with high plasticity. If it's silt with low plasticity, then we have ML. Clay with low plasticity, we have CL. Organic material with low plasticity, OL. Silt with high plasticity or elastic silt, ML. Clay with high plasticity or fat clay, CH. And organic material with high plasticity, OH. And if it's highly organic soil, then we use PT. You can see different soil type, the symbol, which one has a higher or better drainage, which one is a better option with respect to workability, which type of soil is suitable for subgrade application, and which one is more suitable for surfacing. Just remember that when we have well-graded larger particles, it provides better drainage. So coarse material, better drainage. Fine material, low permeability. So not good, poor drainage. Workability, well-graded material provides better workability. When we have well-graded material, it provides better workability because a well-graded material is when we have same amount of particles with different size. So we have fine, intermediate, and coarse particles. So particles with different sizes move along each other and provide a better compaction, a better workability. High plasticity has a poor workability. Particles stick together and it doesn't work well. Well-graded materials, especially well-graded gravel, is an excellent option for subgrade. Generally speaking, fine material with high plasticity are not good options for subgrade. This slide provides information on the allowable pressure and bearing capacity. So as you can expect, bedrock provides a higher allowable foundation pressure and it has higher lateral bearing capacity compared to sedimentary and foliated rock. So this is the way that we observe a decrease. Then we have gravel, sand, and then fine material with lowest bearing capacity and lowest allowable foundation pressure. Okay, now we want to look at the classification provided by OSHA. OSHA is the main federal agency charged with the enforcement of safety and health legislation, and its mission is to assure safe and healthful working conditions for working men and women by setting and enforcing standards and by providing training, outreach education, and assistance. What we are looking at is the excavation standard. A scope of this standard, excavation standard, applies to all open excavations made in the earth's surfaces, including trenches, surface encumbrances that would create a hazard, and protective systems. So in this standard, you can find all of these: the scope, application definitions, specific excavation requirements, requirements for protective systems, and in the appendix, you can also see soil classification. This is what we want to look at. OSHA Soil Classification 1926 Subpart B, P, Appendix A is what we are looking at. This appendix applies when a sloping or benching system is designed in accordance with the requirements set forth in as a method of protection for employees from cave-ins. So OSHA Standard 29, that's Title 29, refers to the label title for the Code of Federal Regulation. Construction is covered in Part 1926. The excavation regulations are found in Subpart P and in Section 652, 652. So, we are looking at OSHA's soil classification. Soil classification system means a method of categorizing soil and rock. Based on OSHA, we have 4 types of soil. It starts with the most stable. So we have a stable rock. And with a decrease in stability, we will have type A, type B, and type C. So the most stable type of soil is a stable rock. Then with a decrease in the stability, we will have type A, type B, and type C. This categorization is based on properties and performance characteristics and environmental conditions of exposure. So first of all, we have the highest stability OSHA stable rocks, which is consisted of natural, solid mineral matter that can be excavated with vertical sides. That is the only category that can be excavated with vertical sides and remain intact while exposed. It's usually identified by a rock name such as granite or sandstone. With a decrease in stability, we have type A. Type A is a cohesive soil that has an unconfined compressive strength higher than 1.5 tons per square foot. So this is the mechanical characteristics, but we also need to pay attention to the environmental exposure conditions. So first, we need to look at compressive strength. Then we also need to look at the environmental conditions. No soil is type A if it's fissured, subject to the vibration of any type, has previously been disturbed, is a part of a slope, is layered system where the layers dip into excavation on a slope of 4:1, or it has seeping water. So first we need to check this one, then we need to check this. With a further decrease in stability and a compressive strength lower than 1.5, higher than 0.5, we will have a soil that is type B based on OSHA's classification. Angular gravel, silt, loam, previously disturbed soils unless otherwise classified as type C, soils that meet the unconfined compressive strength or cementation requirements of type A but are fissured or subjected to vibration, dry, unstable rock, layered systems sloping into the trench at a slope less than 4:1. And then with, again, further decrease in the compressive strength or stability, we have soil type C, which has a compressive strength, unconfined compressive strength of less than 0.5 TSF. Granular soil such as gravel, sand, loamy sand, submerged soil from which water is freely seeping, and submerged rock that is not stable. Material in a sloped layer system where the layers dip into the excavation or have a slope of 4:1 or greater. We also have a structural classification. So what we talked so far was the classification for cohesive soils. For cohesive soils, we have bedrock A, B, and C. We also have a structural classification. Based on the structural classification, soil with less than 15% fines is considered granular soil, which is mostly gravel and sand. Cohesive soil is the soil that has plasticity. Granular cohesionless soil has more than 15% fines, but with low plasticity or no plasticity. Fissures are identified visually or indirectly by tendency of clay with an unconfined compressive strength higher than 1.5 TSF to break into small pieces between 1/4 of an inch and 1 inch due to microfissures when disturbed. So, to summarize the OSHA's classification, we have a soil sample using a structural classification. We call that soil a granular soil if it has less than 15% fines. If it has more than 15% fines with no plasticity, then it's granular cohesionless or silt. So more than 15% fines, but it's fines with no plasticity. That is silt. Here we have less than 15% fines. So it's a granular soil and it's basically sand and gravel. The third option is when we have more than 15% fines with plasticity. So it's clay. And that's when we look at unconfined compressive strength to see if it's considered type A, B, or C. And this is how we classify soil for excavation based on OSHA. Here also you can see soil conditions affect the choice of the protective measures that we need to take for excavation. And based on OSHA's classification, we have type stable rock, that is the only one that we can do vertical excavation. Then we have type A, B, C, and here are the maximum slope and the slope angle. Let's go over more examples. We're going to go over the classification for soil number 1, 2, 3, and 4. Let's start with soil number 1. We have to look at percent passing from sieve number 200 for step 1. Percent passing from number 200 is 2%. Which is less than 50%. So the answer to our question is yes. Less than 50% passes through sieve number 200, which means that we have a coarse grain soil. So now that we know we have a coarse grain soil, we need to see if more than 50% of this coarse section is gravel or not. So we need to calculate percent of gravel divided by percent of coarse. Percent of gravel retained on number 4 is 100 minus 94%. Percent of coarse material is 100 minus 2. Divide 6 by 98 and multiply by 100, you get 6%. So the coarse fraction larger than number 4 is 6.1%. And the answer, more than 50% of coarse fraction is larger than number 4, is no. It's 6%, so it's less than 50%. So it's mainly sand. Now we need to look at percent passing from number 200 again, which is 2%, and it's less than 5%, which means that we have clean sand. We need to see if it's well graded or poorly graded. We have CU and CC. CU is 7.48, which is yes, higher than 6, and CC is 1.52, and yes, it's between 1, 2, 3. So we have a well graded sand. Sample number 2, we start by looking at percent passing from number 200. In this example, it's 70%, which is less than? No, it's not less than 50%. More than 50% is passing through sieve number 200, which means that we have a fine-grained soil. When we have a fine-grained soil, what is important for us is the plasticity of material. And we need to look at liquid limit. Liquid limit is 45%. The question is, if liquid limit is less than 50%, the answer to the question is yes, which means that we have fine-grained soil with low plasticity. So we need to answer the question, do we have organic? It says inorganic. And then we need to use plasticity chart. Liquid limit is 45%. And plasticity index is 45 minus 15, LL minus PL. So we have 45% our liquid limit and 30% our PI. Our point is above the A line. So this one is satisfied. PI is 30%, which is more than 7. So both statements are satisfied, which means that we have lean clay or clay with low plasticity. Soil number 3, percent passing from sieve number 200, 80%. The answer to the question is no, we have a fine-grained soil. So in the next step, we need to look at liquid limit. Liquid limit is 60%, means that we have high plasticity. So we're going to use letter H to describe our soil. Organic? No, our sample is inorganic. And then we have liquid limit of 60%. PI, plasticity index 60 minus 40 gives us 20%. And our points is below A line. So this is not satisfied above, but this is satisfied. Plots below A line. And remember, this is OR, so if one of these statements is satisfied, we know that it's the correct symbol. So the final answer is silt with high plasticity or elastic silt. Soil number 4, we start by looking at percent passing from sieve number 200, which is 10%. Is 10% less than 50%? Yes, which means that we have a coarse-grained soil. Now that we have a coarse-grained soil, we need to see how much gravel we have. Do we have more gravel or do we have more sand? So we need to calculate coarse fracture larger than number 4. And that's percent of gravel divided by percent of coarse material. So this is how much gravel we have. 100 minus percent passing from sieve number 4. This is how much coarse material we have. 100 minus percent passing from sieve number 200. Divide 10 by 90 and times 100. So the answer is 11.1%. Is it more than 50%? No, which means that we have sand. More sand compared to gravel. So now that we know we have mostly sand, we need to again look at the amount of fines we have in our sand. So we go back to percent passing from number 200, and it's 10%, which means that it's between 5 to 12. So now we need to first answer the question, is this sand well graded or poorly graded? And then we also need to see if we have more clay or silt. So in order to answer the question that if this sand is well graded or poorly graded, we need to check these two statements. Cu is 6.85, which is higher than 6, so this is satisfied. Cc is 1.14, which is between 1 to 3. So we have a well-graded sample. So we have SW, but we also need to know if it's clay or silt. And in order to do that, we need to use the plasticity chart. Liquid limit is 32%, plastic limit 15, which gives us a plasticity index of 17. So our point is above A line. It's above A line, and PI is higher than 7, which means that we have clay in our sample. And the final symbol for this soil is SWSC. Now, in order to practice, you can find the symbol for soil number